Okay, so I'll go ahead and get started then. Um, so I think, as everyone knows, we have Lab 2 due on Friday, and Exam 2 is on Monday. So today I'm just going to review for the exam, and I can answer questions about Lab 2 as well. And probably we'll finish up early, and then you'll have the rest of the time to work on the lab or to study for the exam. So let's see. Okay, so hopefully you should be able to see. Oh, hold on a minute. I forgot to reduce my resolution. Sorry, just give me a moment. Okay. Okay, so hopefully you can see the slide there. So we had a few questions about the lab. Sorry. Forgot to confirm the resolution change, so it reverted. Okay, there we go. Okay, so I've had some questions about Lab 2 with regard to the timing. So I think the easiest way to handle the timing, especially for part 3, in particular for part 3, where you have different CFA and CPOL values, is when you read CFA and CPOL at the beginning of your program, you can use the combination of the two to determine the sequence of things that you wait for each transaction. And so for each transaction, you're always going to wait for the first thing that should happen is you should have a falling edge of the SS, slave select. And then the next thing you wait for is going to depend on CFA and CPOL. And assuming I did this correctly, if CPOL is 0 and CFA is 1, or if CPOL is 1 and CFA is 0. So basically, there's two cases. After SS drops, you're either gonna look for the next rising edge after that of the clock, or the next falling edge, and that depends on CFA and CPOL. So if CFA is 1 and CPOL is 1, sorry, if CFA is 1 and CPOL is 0, then you're going to look for the falling edge of the clock. And if CFA is 0 and CPOL is 1, then you're going to look for the falling edge of the clock as well. So basically what that means is that if CPOL and CFA are equal to one another, if they're both 1, I'm sorry, if they're not equal to one another, sorry, if they're not equal, so if your CFA and CPOL is 1, 0 or 0, 1, then you're going to look for the falling edge of the clock after slave select drops, and then every falling edge after that. And that's when you'll read the data. So you wait for the slave select to drop, which will signal a transaction, and then after that, you're looking for the following falling edge of the clock, and then subsequent falling edges of the clock. And for each one of those, you read the data, MISO and MOSI. I think that's the easiest way to think of it. If CFA and CPOL are equal, if they're both 0 or they're both 1, then you look for the rising edge of the clock. And you read the data on every rising edge, and I think that's the easiest way. I've never actually thought about it to that level, but I think that's a way to do it. Again, if they're different, which they are here, for instance, in the upper right hand corner, then you've got SS will drop, and then after that point you're looking for the next rising edge. Sorry, the next falling edge, because the next rising edge is when, in this case, the data is changing. Sorry, the next falling edge. Sorry, hopefully I'm not confusing you more. So to repeat that again, if CPOL and CFA are different, then after the slave select drops, you're going to look for the falling edge of the clock, the next falling edge, right? You don't want to look at the rising edge because in this case, that's when MOSI and MISO are changing. Down in the lower left-hand corner, CFA and CPOL are again different, and in this case, slave select drops, and you look for the falling edge of the clock and every falling edge after that during the transaction, and that's when you read the data. So, and then of course, if they're equal, if CFA and CPOL are both 0 or both 1, then it's the rising edge of the clock. So, for example, in the upper left-hand corner, SS drops, and then you're looking for the, the next rising edge that happens after SS drops, and that's where you'll read your data. So that's going to ensure that the data is nice and stable when you read you read the data on the edges that are indicated here. That will ensure that you're not reading the data when the data is changing. So if you read on the edges that are indicated here, that should ensure that the data is stabilized for a half clock cycle before you read it and a half clock cycle after you read it, which is ideally when you want to sample the data. And when I say sample, in your code, what that means is you would find the time that you want to read using edge at, and then sampling it involves calling the signal at, signal at. Yeah. So you look for the time of the edge, and then you read the signal at that time, and that's when you're sampling the signal. So hopefully that makes things a little bit more clear. The other thing I wanted to mention too, and I don't think I mentioned this when I described the lab in the lecture. I might have, but I'm not sure if I did. And if I did, I might not have emphasized it. But if you look at the test cases, there are cases where there are more than one transaction. So you have to be careful with the way that you structure your loops. You have to design your code assuming that you can have multiple transactions. So in other words, multiple falling edges of slave select. So just keep that in mind. Like, when you think about like how many bits to read during a transaction, you could base that on how many cycles slave select is low, or it could be just you could be counting multiples of 8. Of course, if you do that, you have to make sure that you read the number of for part 2 and part 3. You have to ensure that you know how many bits to expect inside the transaction based on the data in the packet or in the transaction, the second byte of the transaction that comes across for the streaming transactions. So just be careful of that. And I can't think of anything else at the moment to look out for. But if you have any questions, feel free to email us. Okay, so now let's switch gears to quiz 5, which was due today. It's a good question. CPOL and CFA don't change between transactions. No. As far as I know, let me check if Charles isn't here. As far as I know, and I believe it's written in the README for the lab, the CPOL and CFA do not change in each test case. So they're consistent. In real life, they don't change because whenever you hook up a peripheral to a processor, that peripheral is going to have a fixed, CFA and CPOL. So, even in practice, you wouldn't have to worry about those things changing. It's kind of just the way that you initialize the channel. All right, so let me now switch over to quiz 5, right? Yes. Okay, so quiz 5 was on queuing theory. Question 1. Hopefully you can see my quiz 5 slides here. What are the properties of a DM210 queuing system? This is something you just have to look up. D stands for deterministic and M stands for exponential. And it's important for you to know that the first slot is the arrival distribution and the second slot is the service distribution or service time distribution. The third slot in the name of the queuing system is the number of servers, and the fourth is the capacity. And so in this case, the answer is deterministic arrivals, exponential service time, 2 servers, capacity 10. These other answers that are wrong were just the result of me just kind of swapping value or swapping phrases inside of each of these answers. So for example, you could see in the second one, I said deterministic service time and exponential arrivals, and those are out of order. And on the second two, I had 10 servers, capacity 2 instead of 2 servers, capacity 10. Number 2, assume a queuing system on average contains 25 customers and has a waiting time of 10 seconds. What is its average arrival rate? This is an application of Little's law, so it's L equals lambda W. So you set L to 25, and in this case, you know L, and W is 10, the waiting time. And what's the average arrival rate? And then you just solve for lambda, and it's 2.5 customers per second. The waiting time is the time that the customer spends in the entire queuing system. Remember, the queuing system includes the queue and the servers together. So if you say W, you're not distinguishing between time you wait in the queue and the time that you're being serviced. We had a parameter called WQ, W sub Q, that was specific just to the what the waiting time is in the queue, and that's fine. I mean, you can compute that, but normally if it's just W with no subscript, it's the total waiting time. Assume X is an exponentially distributed random variable with rate equals 0.25 events per second. What is the probability that that X is greater than 10? This is you have to use the complementary cumulative distribution function, which is the really simple version. Actually, it's just e raised to the negative lambda t. So you plug in you plug in lambda, which is 0.25, and t, which is 10. I can't tell you how many times I screw these things up when I plug in these numbers in. But this one turns out to be 8.2%. Now it's useful, I think, to do a sanity check when you get an answer like this, because if you're getting, let's see, 0.25 events per second, that's basically means that 4 seconds per event is your average. You want to know what the probability is of having to wait 10 seconds or more than 10 seconds between events. Okay, so the average is 4 seconds per event. What's the probability that you're going to wait more than 10 seconds? I'd say pretty darn low. 8.2%, that's actually a little bit higher than I would expect it to be, but I think that's a reasonable number. Okay, assume the Pittsburgh Steelers score touchdowns according to an exponential distribution with rate 1.1 touchdowns per quarter, while the Los Angeles Rams score touchdowns according to an exponential distribution with rate 0.95 touchdowns per quarter. What's the probability that either team will score a touchdown in the first quarter? So notice that I changed the rate, the time units for the rate to quarters instead of seconds. So in this case, this is the rule that says that if you're looking for the minimum, you're looking for a random variable, a new random variable. So this is basically a third. We have 2 random variables. We're coming up now with a third one that represents the minimum time of an event happening, or of an event being generated by the first 2. Hopefully that's an accurate way to describe it. So in this case, we're going to add, to do that, you add the lambdas together, and you create this third exponentially distributed random variable. So in this case, the new lambda is 1.1 plus 0.95, 2.05, and then you're calculating the cumulative distribution function, which is the probability that t will be less than or equal to a value that you give it t, which in this case is 1 because it's 1/4 and our time unit is quarters. So it would just be 1 minus e raised to the negative lambda t. And like I said, t is 1, lambda is going to be 2.05. So the answer is 87.1%. Assume the Pittsburgh Steelers score touchdowns according to a Poisson process with rate equals 1.1 touchdowns per quarter. What's the probability that they will score 3 touchdowns by the third? Okay, well, I mean, sorry, question? Okay. So what's the probability? Well, I mean, I would say pretty good. Right? 3 touchdowns by the third quarter, 1.1 touchdowns per quarter. Let's say pretty good. So you use the Poisson function, which is lambda t raised to the nth power over n factorial times e raised to the negative lambda t. So in this case, you have to plug in 3 separate values here. We've got t, which is 3, lambda, which is 1.1, and n, which is 3. And I screwed this up several times. I switched them around. Just be careful where you plug these numbers in. And the answer is 22%. Seems low, but seems low. Okay, assume the Pittsburgh Steelers score touchdowns according to a Poisson process with rate 1.1 touchdowns per quarter. What's the average time between touchdowns? This is an easy one, actually. This is just you just take the mean is the inverse of lambda, so 1 over 1.1. It's 0.9 touchdowns, 0.9 quarters per touchdown. So keep in mind that with the exponential distribution, the random variable represents the time between events, whereas the Poisson process is giving you a probability. So just keep that in mind. Assume an airport has 4 security lines. Passengers entering the terminal are dispatched to each line at a 25% probability. If passengers arrive according to an exponential distribution every 10 seconds on average, what is the minimum service rate needed at each of the 4 security lines? So for this, we're going to use the splitting property. And so basically, we just have to make sure that if you add up the lambdas of each line, it has to equal at least 1 over 10, because 1 over 10 is the rate. Because I didn't give you the rate, I gave you the mean, so you have to take the reciprocal of that. And so you solve for lambda sub line, which is basically just 1/10 divided by 4, which is 0.025. So that's again, that's the splitting property. Just make sure you're familiar with that. What is the expected number of customers waiting in the queue in steady state for an MM1 queue with lambda 0.2 per second and mu 0.3 per second? Okay, so now we've got lambda and mu because now we're finally talking about a queuing system. All those other questions weren't about queuing systems except for the Little's Law one. So we have lambda and mu. Remember that lambda is the arrival, mu is the service rate. Lambda has to be less than mu. If not, then you've got a problem. Oh, go back to the previous question? Sure. Yep. Let's see. Quiz 5. Yes, this question? Sure. Yeah, so this is the splitting. So this basically says that, oh, well, I'm sorry, this is not splitting actually, right? Yes, it is. Yeah, it's splitting because you have 4 security lines, you've got passengers coming in the terminal, and they're being split off into 4 lines. And so now, by the way, the reason this works is because the reason it's kind of simplified here is because each line has an equal probability, 25% probability. Right, so there's 4 lines, and each line, each incoming passenger goes to one of the 4 lines with a at 25% probability. So as a result, I didn't have to weight the lambdas there. Does it make sense? Okay. Yeah. Yeah, and I'll revisit this too, and I'll switch to the other slides too, and I'll go back to this on the in the main lecture too, just to go over this again. Yeah, it's a little confusing. Okay. Okay, so what's the expected number of customers waiting in the queue? Now, notice that I said waiting in the queue, not waiting in the system. So lambda is 0.2, mu is 0.03. So you have to use the L sub q, which is rho squared over 1 minus rho, which is also equivalent to, if you take rho and you replace it with lambda over mu, and you should get lambda squared over mu times mu minus lambda. So you can use either one of those. If you use the rho version, then you have to calculate the ratio of lambda over mu. If you use the lambda mu version, then you're just plugging the values directly in. So it should be 1.3. Now you might say, how can you have 1.3 people waiting in line? Well, that's the average. What's the expected steady state waiting time for an MM1 queue with lambda equals 0.2 per second and mu equals 0.3 per second? So in this case, this is the waiting time, not the previous question was number of customers in the queue. This is waiting time. Right. So for the waiting time, that one is rho over lambda times 1 minus rho, which that's a strange way to write it because you've got rho and lambda in there. But you can also, it simplifies to 1 over mu minus lambda. And so that's just 10, ends up being 10 seconds. And that's the whole system. That's not just the queue now. This is the waiting time. It's how long it takes to get through the queue and to be serviced. What percentage of time will the queue be empty for an MM1 queue with lambda equals 0.2 per second and mu equals 0.3 per second? I had several questions about this one. This one was tricky because I think some of you just calculated p sub 0 for this, but you have to add p sub 1 because you're looking for the case where you have to have at least 2 or more. You have to have at least 2 customers in the system in order for 1 to be in the queue when you have 1 server. So you have to add p sub 0 and p sub 1. So p sub 0 is 1 minus rho, p sub 1 is 1 minus rho times rho, and that ends up being 56%. So that's not bad. Okay, that's quiz 5. All right, now let me switch over to, so let's see, should I start? Let me start with queuing theory since we just got done talking about that, and then I'll go back to real-time scheduling. So let's share queuing theory. Okay, so I'll go through this. Hopefully you should see the queuing theory slides. I'll go through this kind of fast. Yeah, there they are. I'll go through this kind of fast because we went through this on Monday too. But if you have any questions, please ask. So the remember that the queuing system includes the queue and the servers, and there's the notation, which is for a queuing system. It tries to include all the information you know in order to do the analysis. So you've got the arrival time and service time distributions, followed by the number of parallel servers, and then optionally you can have a system capacity and a queue discipline. Little's law is real simple. It's just L equals lambda W. L being the number of customers in the system, not in the queue, but in the whole system. Lambda is the average arrival rate, and W is the time in the system. Notice there's no mu here because mu is something that you would need to use to calculate W. But if you just know W, then you can just apply Little's law. So in this case, like if you have a school with 6 grades and 30 new students enroll each year, you've got a waiting time of 6 years and you're getting 30 new students per year. So you want to know the total number of students enrolled in the school is 180. The exponential distribution is modeling the inter-arrival times. So you've got a rate, which is lambda. The average time between arrivals is 1 over lambda, and the variance is 1 over lambda squared. The variance is, I think, the more kind of the interesting part, because it says that it means that if lambda is smaller, it increases the variance drastically, which means that the the distribution flattens out with lower values of lambda, which I tried to show there in that plot that I generated from MATLAB. So what that really means is that if your rate is lower, it just means that your arrivals are kind of more unpredictable, I guess, or spread out. Right, and then we've got the PDF, the CDF, and the CCDF. The CDF and the CCDF, I think, are pretty obvious. I mean, it's basically it's literally just an exponential function, e raised to the negative lambda t. But the CDF has that 1 minus, and the CCDF just is e to the negative lambda t. And then the probability density function isn't really useful for much other than integrating it to get the CDF, but it's lambda e lambda t. It's basically that's the derivative of the CDF, essentially, and it gives you a relative probability. So I guess some examples here. Skip over that. Okay, so this one is that property that says if you're looking for the minimum, or if you're synthesizing a new random variable that represents the minimum of a set of other random variables, then you can just add up the lambdas and create a new random variable. So this one's useful when you're looking for when you can, the first event to happen in a set of exponential random variables. We use this in the birth-death process because you've got lambda and mu, which is the rate at which you get a new customer, or you shed a customer, you service a customer, and so that since either outcome can occur within any state, you add together lambda and mu to get the expected time you're going to spend in a state. Okay, then Poisson process is probability of n events occurring by a time t with rate lambda. We didn't really, I don't know if you noticed this, but we didn't really use the Poisson process when we derived the queuing system equations. So you might be wondering why, where do we use the Poisson process? How does that fit in to queuing theory? It does. We didn't get to that point. So the Poisson process is kind of fundamental to queuing theory, but we didn't get into it enough to use it. But I just want you to be familiar with it in case you need to use it. So the whole purpose of this lecture is to get you familiar enough with this stuff that if you need to apply it for a more complex queuing system, it wouldn't be hard for you to do since you know all the the fundamentals. But a Poisson process is a way to basically count events And so you've got this additional parameter n, which is the number of events, and t would be the time that you're giving, so you've got n events and you've got a time t, and you're calculating the probability of n events occurring by time t with, assuming rate lambda. Okay, and then we talked about splitting. So splitting and superposition, by the way, these are about the Poisson process. So these kind of build on the Poisson process. But so you've got a Poisson process, and every time an event occurs, you assign it to n other, or you assign it to n types of events, and so so let n of t be a Poisson process with a rate lambda. That's the one that feeds everything. And then suppose that each event is labeled as an I-type event with probability p sub I, independent of all else. Let n sub I of t, I 1 to n, be the number of type I events that happen by time t. So you're basically saying, well, okay, I've got one main Poisson process. It generates events, but each event has a certain type, and so I want to calculate, I want to synthesize a new Poisson process for each of the types. And so in that case, you would just multiply the probability of the type by the original lambda, and then you could apply, and then that's like a new Poisson process that's applied only to the type. And then they have this thing superposition, which is kind of the opposite, where you've got a set of Poisson processes and you're trying to generalize the events generated by all of them. And so you can conceptualize that, or you can model that as a Poisson process that has a rate equaling the sum of all the rates of the individual ones. Okay, and then so this talks about how events in a Poisson process are independent. And then we talked about the birth-death process, which is a Markov chain, and it's basically states. You can only be one state. You can only be in one state at one time, and from each state represents the number of customers in the system. And again, that includes the queue and the servers. And lambda is the rate at which you'll increase the number of customers in the system, and mu is the rate at which you will decrease the number of customers in the system. And so this is the foundation of how you develop these queuing system, or the queuing theory. It has this weird rule about flow balance, and so everything is based on this notion that the flow in and out of every state should be equal. Now, you might say, oh, wait a second here. Yeah, flow, I mean, what is a flow? What does that mean? The flow, to be honest, this is not, I found that this wasn't very well defined in the textbook that I used. But you'll notice from the equation that the flow evidently is the rate multiplied by the probability of being in a state for each transition. So the lambda plus mu is the times Pn is the flow coming out of state n, but then you have flow coming into state n from n minus 1 and n plus 1, again, you'd be multiplying the rates times the probability. I actually tried to look this up. I tried to figure out why the rates, these are exponential rates, why are you multiplying rates against probabilities here? I never did. I couldn't find the answer to that. But this is the flow, though. This is, I mean, obviously, it represents the flow. It's the kind of I guess a generic term that represents the flow. The flow in has to equal the flow out. And so for any state other than 1, it's the 2 incoming flows have to equal the 2 outgoing flows, and then state 0 is a special case where you just have 1 incoming and 1 outgoing transition. So, so you start with that equation, and then from there you can basically calculate the probability of being in any individual state as a function of lambda and mu and the probability of being in state 0, which was kind of cool how that worked out. We built that up incrementally, sort of from the bottom up. We did it it's an inductive proof. So basically, the probability of being in state n is probability of being in state 0 times lambda over mu to the nth power. And then in order to calculate the probability of being in state 0, that took some effort. Sorry, my animation order is wrong there. So what we ended up with is we discovered that p sub 0 is 1 minus rho, and that was done through a lot of steps. The weirdest one being oh yeah, well actually this one wasn't the bad one. It was the waiting time one actually, or the expected number of customers in the system actually was a stranger one actually. But yeah, so p sub 0 is 1 minus rho, and then p sub n is 1 minus rho times rho to the nth power. That's a pretty nice result. This obviously gets more complicated for different types of queuing systems, but in this case, it actually kind of reduces down to a fairly simple equation. And I tried to put boxes around all of the final. Let's see. Let me change. I tried to put boxes around like the final equation, the one that you'll be using. Now, for the number of expected customers in the system, yeah, this is the one that was a little stranger. We had to do this thing where we calculated, we inexplicably took the sum. We had to eliminate the summation, and doing that can be tricky sometimes. And so in order to do that, we had to factor out rho from the summation. It's like, well, how did you know to do that? Well, we did it, and it just so happened that by doing that, we ended up with a derivative of another summation that we had a closed form solution for. So we were able to go back and then take the derivative of the original closed form summation and get the second summation. So we had one summation. We had a nice expression for one summation, but we needed one for another summation, so we did it through this derivative trick. And in the end, we ended up with L, which turned out to be a very nice result. L equals rho over 1 minus rho. So that's, I thought that worked out really well. So I showed this result that, you increase your arrival rate, and as expected, the number of customers in the system increases exponentially, which not surprising. And then we did a variation on this that turned out to be pretty easy, simply because it turned out to be a function of L, which we already calculated, and P0, which we already calculated. So this one was pretty easy. This was the expected number of customers that are just in the queue. So this was a variation on this, so we called it L sub Q. And then the waiting time, the only way to get that is through Little's law. So there's waiting time in the system, waiting time for the queue. We got the waiting time using Little's law, which is very simple after having done all the hard work to get the number L, basically L. Okay, and so here's an example. I didn't get to this last time, so I'm going to go through it now. Miss Cut runs a one-person hair salon. She doesn't make appointments. Uh-oh, what was that? That was my MATLAB, sorry. She does not make appointments, but runs the salon on a first-come, first-served basis. She finds that she's extremely busy on Saturday mornings, so she's considering hiring a part-time assistant and even possibly moving to a larger building. Customers arrive according to a Poisson process with a mean arrival rate of 5 per hour. Customers are always willing to wait, meaning that you don't have some queuing systems can have like customers that will leave if the wait is too long. But in hardware, by the way, that would happen if you run out of your queue overflows, for instance. Customer processing time is exponentially distributed with an average rate, with an average of 10 minutes. Okay, so we have, I guess, lambda is 1 over 5, and mu is 1 over 10 based on this. Right. Right. So rho is 5 over 6. Oh, sorry. Yeah, 10 minutes. This is hour. Yeah, sorry. 5 per hour. So our time units are hours. So Arrival time is lambda, that's 1 over 5. Customer processing time is average of 10 minutes, which is 1/6 of an hour. So, yeah, so 6 per hour, or is the average, or 1 over 6 is the rate. Yeah, so rho is 5 over 6, and so L is 5, L being the average number of customers in the system, and L sub Q, which is the number in the queue, is 4 and 1/6, and those are just based on the L and the L sub Q. Sorry, I just plugged those into, yeah, L is rho over 1 minus rho. Oh, sorry. No, L is rho over 1. Yeah, rho over 1 minus rho. And L sub Q is rho squared over 1 minus rho. So hopefully those should be correct. So we get an L and an L sub Q. And then if you calculate P sub 0, it would be 1 minus rho, which is 5, which is 1, well, it's 1 minus 5/6, which gives you 1/6. Which means that you spend 16.7% of the time in state 0, meaning that cut is idle, meaning she's not doing anything. Now remember that if you're in state 1, she won't be idle, but there'll be no one in the queue. And if you're in state 2, then she won't be idle, and there'll be someone waiting. Okay, so cut's waiting room has 4 seats. The probability of finding no seat when a customer arrives. Now this, I don't know how they got this expression. So according to the book, the probability of n being greater than or equal to 5 is rho to the 5th power, which is 40.2%. I don't know where that came from. In fact, I went back and I looked at it again, and the book was like, well, that should be obvious. I was like, no. So I don't know where that came from. However, I know another way to get the same answer. All you have to do is find the probability of being in state 1 up to state 4. Okay, because if you're in state 4, you're going to have 1 customer getting his or her haircut and 3 in waiting, right? Yeah. Right. Now, if you're in 5, yeah. So if you're in 5, if P sub 5 would be 1 customer's getting the haircut and all 4 seats are taken. So so 1 minus the probability of 0 minus the probability of 1 minus the probability of 2 minus the probability of 3 minus the probability of 4. If you work that out, you get the same answer, which is 40.2%. So 40.2% of the time, you're going to have all 4 seats taken. Right? If n is greater than 5, so you're going to have at least greater than or equal to 5. Yeah, so like, because you don't want to look at the time that you've got no one in the shop, or no seats taken, or 1 seat taken, or 2 seats taken, or 3 seats taken, right? So seems like it should be seems like you had to subtract P sub 5 as well. Maybe I might have done that actually when I worked it out. Let me double check that. No, I just went up to 4. Oh, that's interesting. Now I'm questioning that. Yeah. Anyway, I'll look into that. That one's a little tricky. I won't ask anything that tricky, or if I do, I'll provide more explanation. But yeah, that's all that's all I've got for queuing theory. If you got any questions about it, feel free to post them. Anyone still here? Yes. Okay. All right. Okay. So now I will revisit real-time scheduling because the exam will cover that as well. Okay, so luckily this exam is only, you know, there's less material for this exam than there were for the last one. It's just on real-time scheduling and queuing theory. So I mentioned with real-time scheduling that operating systems are responsible for scheduling the CPU, determining which processes get to run, but they don't make any guarantees about performance. So you know, you run something on Linux and you don't have any promises. So you know, might think, well, you know, really, why not? I mean, Linux should be able to do that. It should be able to make a promise about how fast it can run, especially if you know the worst case execution time of the task. But it's hard to do that. And the reason is simply because the number of ways you can run the tasks on the CPU is exponential. So that's the reason. Let's see. So one issue is the worst case execution time. How do you know what the worst case execution time is when you have uncertainties? You know, you've got cache misses that are non-deterministic, timer, you know, interrupts, external interrupts coming in. What else? Oh, and there's data-dependent behavior. Sometimes, you know, depending on the input, your program may take a little longer to run. So one way to characterize this is to do it empirically, which is to basically just run it a bunch of times and measure, and then look at the numbers, look at the statistics of the runtime. And so, for example, if you assume that the data is normally distributed, you can calculate the mean and the standard deviation, and from that you can calculate the maximum runtime with a specific level of confidence. The problem is that, and this is a big deal because programs will their behavior can be much different depending on the data that you give them. So it would be better if you try to just if you treat this as a black box, then you end up with a pretty loose measurement. But on the other hand, if you have some information about what mode the program is running in, then you can statistically model the runtime of each mode, like of each class of behavior, and then you can get a tighter estimate of the max runtime. So in this case, you know, we had the same data when we just looked at it all together. Let's see, I have an example here. Yeah, so say you have a task, you run it 10 times, and you get a bunch of run times ranging from 10 milliseconds up to 32 milliseconds. And so at 99.9% confidence interval, assuming it's a Gaussian distributed random variable, and using a confidence of 99.9%, then your worst case execution time is going to be 3.09 times the standard deviation, which is 9.2, and you're adding that to the mean, which is 48.9, which is huge compared to the maximum value we observed in those 10 runs. I mean, we saw 32 milliseconds, and now we're estimating 48 milliseconds. But if you assume the first and second measurements are generated from two separate control paths, two different modes, then you can model them separately, and you get a tighter measurement that way. You can just group the first and the second runs, and you get tighter standard deviations for each. And so in that case, you're just looking at the max the estimates of the individual distributions. So you had one group that had a mean of 12, one group that had a mean of 29, and then the first group had a 1.6 standard deviation, and the second group had a 2.9 standard deviation. So at 99.9% confidence, you got estimates of 16.9 and 38 for those two. So 38 would be the max overall. So 38 is less than 48. That's pretty darn good. I mean, that's right. That's like 22% better. So that's again, this is a kind of even that's a very simplistic way of measuring it. But the point is that it's tricky to get a worst case execution time. But it's important to get it, because if your real-time scheduling algorithm is only as good as your worst case execution times you give it. So we talked about tasks being in different states. I probably didn't explain this as well as I should have. So the idea is that you can have a task that's ready, that's waiting to be executed, or is asleep, that it's running but it's not ready to be executed for whatever reason. It might be waiting for an input, and then you can be executing. And so here's an example of 4 different tasks, and I showed that there's n factorial ways that you can schedule these on the CPU, and even then, it's assuming that the tasks are not preemptible, that when you start running a task, you run it to completion. And there's 24 different ways to schedule, and there was only 2 that actually gave us actually had all 4 tasks meeting their deadlines, which is pretty wild. And so those 2 happen to correspond to the earliest deadline first and least slack first. I don't know what you want to call those, algorithms, rules of thumb. So in the slack, by the way, is the difference between the execution time and its deadline. Now, the problem with this, by the way, was that it's very uncommon for real-time tasks to be one and done. Usually they're periodic. And now when I took this class, I was like, why periodic? I don't understand, like, in what scenario would you have a periodic task? I didn't understand. And no one explained it to me until I figured it out on my own, and what I found was that the answer was control systems. So control systems, which is what we looked at in the previous lecture, is when you need to anytime you try to control anything in the outside world, you're going to have some sort of periodic task that takes in sensor values and then does some compute and then outputs an output that controls some servo or some system, some valve, or some switch, or whatever the case may be. Now you might be saying, wait a second, the control theory stuff that you showed us, the examples that you showed us, were really simple. I mean, the algorithms that we looked at were like a couple multiplies and a couple adds. Are you telling me that could have an execution time that's long enough to make this scheduling difficult? And the answer is yes, it does, if your period is small enough. Sure, yeah. So we also talked about the time, the Z transform and the sample rate, and if that sample rate is high enough, even if you're only doing a few multiplies, yeah, it could take a while. And remember that you may have to include the effects of the queuing system in there as well, which is why we also looked at queuing theory, which is because if you look at the Atmel M328P, which is the Arduino processor that a lot of people use as a microcontroller, that thing only has like a small handful of external interfaces on it. Has a limited number of pins, so you may have to go through a queue to get signals out to multiple peripherals. And so for that reason, the execution time, you'd have to include queuing delay as well in there. So yeah, absolutely, this is all still very relevant. And of course, you can have a control theory, a control algorithm that does something more complex than the ones we looked at. You could have one that includes some signal, image processing, like for example, that's what Tesla does. the Tesla self-driving car software has to do lane detection on 18 cameras, and it has to do that within its control period. So you can imagine that there's a lot of, and of course, each one of those cameras you have to process all the pixels and extract features. So that takes time. So yeah, this is all still relevant to that. That's why that they put a hugely powerful computer in those cars. And not only that, but it's not an off-the-shelf computer. They designed it from scratch to do just that task really fast. Okay, periodic, let's see. So the periodic has a periodic scheduling. Algorithms require you to give it a set of tasks, each of which has an execution time and a period. The utilization is where you add up the ratios of execution time and periods for all the tasks. Obviously, anything over 100%, or rather 100% times the number of processors, is impossible. Then we talked about earliest deadline first scheduling, which is where you always give the process that has the earliest deadline, the earliest task, the CPU, even if it means interrupting whoever's running on the CPU now. And that may happen, of course, like when you have a high priority task starts a new period, you would obviously override whoever's on the CPU and preempt. The problem with EDF is that you have to constantly reevaluate the priorities of every task as time goes. So the priorities are dynamic. And the problem with that is that you can't really even do that at all. I mean, think about it. How are you going to continuously reassign priorities? Who's going to do that if the CPU is supposed to be running tasks? Who's doing that? No one. Unless you have a dedicated CPU for just that, right? So like, for example, in Linux has this idea of a quantum, which is where it will always interrupt every task, whatever the quantum time is in the Linux kernel. I think it's like 10 a millisecond or 10 milliseconds, something like that. And so it'll always go back to the scheduler after every quantum and reevaluate what's going on. And in a lot of cases, if you're just running one program, like if you just have one ready process on your Linux machine, then the process will get interrupted after the quantum has elapsed, and then the kernel will say, oh, well, there's nothing else to do, so yeah, just carry on, and it'll go back to executing that same task again. But it always interrupts after the quantum, basically just to get into the kernel, to check and see if nothing needs addressing, or there's no other higher priority tasks that just came to be ready. The problem is that whatever that quantum is going to be the granularity for reevaluating priorities in an EDF scheduler. And so unless that quantum is very small and you reevaluate priorities at a very fast rate, then you may end up missing something, right? You may end up being too late to notice a task has become available that has the highest priority or higher priority than the task that's running. And the problem with turning the quantum down is if you turn it down too low, you end up spending all your time inside the scheduler, inside the operating system, as opposed to actually running the task. So it becomes inefficient. So you can't really, it's not really practical to do it. So that's why EDF doesn't work. And EDF by its nature, it's not really feasible to, I mean, you could build the schedule ahead of time, but that schedule could be enormous if you have a lot of tasks, because that schedule would have to repeat at whatever the least common multiple of all your periods are. So EDF is just totally not practical, but the nice thing about it is that it's optimal in the sense that as long as your utilization is under 100%, it'll work. For one processor at least, not for multiple. Rate monotonic scheduling is the kind of the one that most people think of, and it just schedules tasks with the shortest period first. And that's a static priority. So I tried to I spent quite a bit of time writing this code that generates these waveforms, because when I looked at this stuff, it was hard for me to visualize it. So I tried to show what's going on using these waveforms. The waveforms are, one per task, and it's either 0 or 1 depending on whether the task is running on the CPU or not. And then, obviously only one task can be running at one time. So of all these tasks you have, at any moment in time, only one of these is 1 and the other ones are 0. So this is an EDF schedule, and then this is the RMS schedule. In this case, utilization was 80%, and both of them successfully scheduled. No deadlines were missed. The problem is, oh, wait a minute. Did I miss a deadline? Oh, yeah, no. I didn't miss a deadline until I switched to this new set of tasks, which was 410, 312, 515. This one didn't have an 80% utilization. It had a 98.3% utilization, which was obviously very close to 100. The EDF just did fine. The RMS didn't. But notice that the RMS didn't miss a deadline until it got to, way over here. So RMS started out okay, but for whatever reason, and I really don't know how to explain it. It's just the way things kind of worked out right there, how the periods sort of worked out. Just task 3 misses deadline. Not on the first period, not on the second period, but on the third period. On the third period of task 3, which happened to be the 1, 2, 3, 4th period of task 2, and the 1, 2, 3, 4, 5th period of task 1, we had a deadline miss. Why is that? I mean, why did it work out that way? I don't know. It just dismissed it. Just drove it too hard. So we talked about the RMS schedulability test. This is, by the way, not the first schedulability test. There have been other ones proposed. I remember when I was in grad school, it was different because they didn't have this one yet. When I was in graduate school, there was this thing called the Liu and Leyland bound. Liu and Leyland were the authors of the original paper that described RMS scheduling back in the 70s, I think 1972. But those guys, even though they came up with RMS scheduling, their schedulability criteria was basically you couldn't go over 69% utilization, or they wouldn't make a guarantee. And it turns out now that that's no longer the case. There's a better bound. This one's better. You can go higher than 69%. And so it's basically multiply 1 plus the execution time over the period, multiply those out over all the tasks, and that number, if it's less than or equal to 0, guarantee schedulability. Otherwise, can't make any promises. And then I mentioned that RMS, there's a caveat. If the periods are mutually harmonic, then that means you can actually get up to 100%. I don't know how common that is, though. That seems kind of contrived. Multiprocessor scheduling is really hard. There's no solution to this, as far as I know. This is an open problem in computer science. There's a couple approaches. There's partition scheduling, which is just basically an NP impossible, assign all tasks, to a specific processor and try to figure it out. Then there's global scheduling, which is what you want, which is when you have a, pool of tasks can go to a pool of processors. One way to do that is the RMS, rate monotonic first fit periodic scheduling. This one has a bound that is the utilization has to be less than or equal to 0.41 times the number of processors. That's a crappy bound, but no one's come up with anything better for that yet. The problem with this algorithm, and you might say, why is it so bad? Well, basically, it's something you do at the beginning. You kind of do a greedy match. It's basically a partitioned approach at the beginning, but you assign each task to a processor based on the RMS, but you do it in a greedy way. And then once you make the assignment, then you keep all those tasks to their assigned processors. So it's kind of, yeah, it's not real smart. Then there's an EDF version of this, and this one is has a weird bound. So the utilization has to be less than M, but also you have to calculate the greatest common divisor of all the periods and then multiply each of those times the corresponding, or multiply the greatest common divisor against each of the tasks' ratio of runtime over period, and you're looking to see if all of those are integers. Why is that? Why do you have to go through all that? What is the deal? The problem with this one is that this one is dynamic, but you're taking the n highest priority. So if you have like 3 processors, you're looking for the 3 highest priorities and scheduling those on separate processors, which isn't necessarily the best way to do it. So that's why it's even though it's EDF, and you think, well, EDF, on one processor it was perfect, but it's not. It's on multiple processors it falls apart. So there's that bound, and that's it. That's all I got for real-time scheduling. So the exam, like I said, will be on Monday. The last exam, I had 15 questions and a 75-minute limit. I had several students complain that was too many questions. I'm planning on reducing that to maybe 12 questions. The problem with that is, of course, if you've only got 12 questions and you miss one, then it's pretty devastating. So I'm not real happy about that, but on the other hand, I don't want to, make you sit through a super long exam, because we wouldn't be able to do that if this was a regular class anyway. So so I think my plan is to do 12 questions. Anything in the slides is fair game. Obviously you can't derive proofs in a multiple choice, but if there's any questions, if I can come up with anything to ask you about the derivations of those queuing theory equations, then I might ask. So make sure you're comfortable with everything in there. And if you have any questions, feel free to email us. Yeah, so, yes, slides for scheduling and queue theory. Yeah, that's all we've got is the slides for those. I have a really good book on queuing theory. I didn't want to. Obviously, I'm sourcing material from multiple books for this course, so I think in total there's like 4 or 5 books. So I didn't want to have, we don't have a single book that has all this in it. That's why Charles and Philip and I are writing a book that will, instead of having a whole book on queuing theory or control theory, which of course you can do and those exist. I wanted to give kind of an introduction to these topics. These are all the things that I think are important for cyber physical systems, which itself is a fairly new, I shouldn't say a new area, but it's becoming increasingly important with all these control systems. I just got a call from a guy that was, he works for a firm, and they're developing a control system for a set of valves for a power plant that just open and close valves based on pressure. And so he sent me this MATLAB Simulink design with the whole system. It had all these nested control loops and stuff in, but it was all just S and Z domain LTIs in there. That was kind of interesting. Just direct application of this stuff. Okay, well, I told you I'd give you some time at the end here to get some work done. So if you have any other questions, feel free to email us, and we'll see you back on. Well, I won't see you on Monday. We won't have class on Monday. It'll just be you'll take the exam on Monday. I'll send an email reminder about that, and I'll post all of these slides on the web as well as this lecture if you want to re-listen to it. Unfortunately, I can't discuss the lab right now because I have to run to pick up my son from daycare downtown. But actually, Charles might. Charles, are you here?
Yeah, if somebody has a question about lab, I can certainly answer it.
Yeah, so I think if I can leave, and I think Charles could probably stick around and answer the question. And I think you guys, I think Adam, you can probably.
Yeah, I have my mic on.
Okay. Yeah. So okay. Well, sounds good. Thanks, guys. I'm gonna drop off. If you have any other questions, if you think of anything tonight, just send us an email.
Charles,